Namaste students, welcome you all to this session. Let us solve few more problems on Poisson distribution. First problem is, on an average, 1 in every 50 valves manufactured by a firm is a substandard. If valves are supplied in packets of 100 each, so a packet has 100 valves. In how many of a lot of 2000 packets would you expect substandard valves? Here first note, it is asked to find how many of a lot of, that is how many items, how many persons, what we must use that. In such cases, that is a theoretical frequency function. Tx is equal to n into p of x. Now here it is a problem related to Poisson distribution because it is given on an average 1 in every 50 valves manufactured by a firm is substandard. Substandard is not standard, not good. If the item is not good, usually we are going to call it as a defective item or a substandard. So here we have to deal with a product which is a substandard. So the product may be standard or a substandard. There are two possibilities. Is it right? So here first we have to see the problem is related to which distribution first. Here the number of defective items in a sample of 100 items or in a pack of 10 items. This is an example for what? Binomial distribution. Now actually this is also a problem on binomial distribution. Let us see why it is a problem on binomial distribution. Here 1 in every 50 valves, that is if there are 50 valves, it is given usually on an average among 50 one is a substandard. So it is the information to find the probability of a valve is a substandard. So what is probability of a valve is substandard? Probability of valve is a substandard, which is equal to P, the parameter P, which is equal to 1 by 50. That is a Q equal to 1 minus 1 by 50. So this is it seems like the parameter P of a binomial distribution, which is nothing but a probability of success. So success is nothing but a valve is a substandard. So here we can define, let X denote the number of substandard valves. Substandard valves. Among how many valves? That is, it is given each packet has 100 valves. And they have told how many of a lot of 2000 packets. That is it is given totally there are 2000 packets. In each packet there are 100 valves. So here the sample has 100 items. That is X denote the number of substandard valves among 100 valves. Right? Among 100 valves. Now this 100 is the first parameter n of a binomial distribution, and P just now we have seen it is given in terms of a proportion. Then a substandard, it is nothing but a success in a binomial distribution. Now here we can observe n equal to 100 and P equal to 1 by 50. P equal to 1 by 50, right? Next here just we can observe once again n is very large, right? N is very large and P is very small. P is very small. For that you can calculate 1 by 50. Here P equal to 1 by 50, which is equal to 0.02, right? And Q equal to 1 minus 0.02, that is 0.98. Now instead of 1 by 50 you can write 0.02. Now you can say P is very small, right? P is very small. In earlier class I told 0.01, 0.02 and all, you can consider it as a small probability. So it is a 0.02. Next here, since n is large, and P is small. Which distribution we can use? Poisson distribution can be used with the help of one of the feature. It tends to binomial distribution tends to Poisson when n tends to infinity and p tends to 0. Now consider for conversion we have to consider the third in that feature third condition lambda equal to n. What is n? N is 100 into p is 0.02, right? 0.02 you will be getting. Now we converted the given binomial problem as a Poisson problem. Let us continue with the probability mass function of Poisson distribution. This implies x follows Poisson in bracket lambda equal to 2, right? Next the probability mass function is P of x equal to e power minus lambda, lambda power x divided by x factorial, x is equal to 0, 1 to up to infinity, which is equal to e power minus lambda, e power minus 2, 2 power x divided by x factorial, divided by x factorial. X is equal to 0, 1 to up to infinity. Now this is the required probability mass function. Next, let us continue. We have to find the first probability. After that, multiply it by n, capital letter n. What is capital letter n? How many packets are there? It is given 2000 packets. Among 2000 packets, how many contain or how would you expect substandard values? So here we have to consider n given n equal to 2000. Next, first find the probability. Therefore, probability of which probability we have to calculate? That is a probability of a packet contain a substandard value. First, it is to be calculated what is the probability of a packet has a substandard value. So, probability of a packet has a substandard value. Now, when do you say a packet has a defective value or substandard value? Usually, if a packet contains one value, defective value or more than one defective value, they are going to say the packet is a substandard, packet is not good. So, here we can write probability of a packet has a substandard value is equal to probability of a packet has at least one substandard value. Substandard value. A packet has at least one substandard value. At least one substandard value, which is equal to probability of x is greater than or equal to 1. Probability of x is greater than or equal to 1. What is probability of x is greater than or equal to 1? 1 minus p of x equal to 0, right? Which is equal to 1 minus p of x equal to 0. In the probability mass function, put x is equal to 0. That is a e power minus 2, 2 power 0 divided by 0 factorial, which is equal to e power minus 2. That is a 0.1353. 1 minus 0.1353 into 2 power 0, 1 divided by 0 factorial, 1, which is equal to 1 minus 0.1353, which is equal to 0.8647. 0.8647. Now it is the probability of a packet has a substandard value. A packet has a substandard value. Now if there are 2000 such packets, how many packets would you expect the substandard values? Multiply the probability by n. Therefore, expected number of packets expected number of packets contain substandard values. Expected number of packets contain substandard values is equal to capital letter N into P of X is greater than or equal to 1, which is equal to capital letter N, that is a 2000, right? I wrote here N equal to 2000. 2000 into 0.8647, which is equal to 1729.4, which is approximately equal to 1729 packets, right? 1729 packets. So here the answer is among 2000 packets, in 1729 packets, we can say they have substandard values, right? Among 1729 are expected to have substandard values. Next, let us move to one more problem. That is here I wrote next problem. Suppose 180 misprints are distributed randomly throughout a book. Go through this word. We are dealing with the misprints. Yes, improper print, misprints. How many misprints? 180 misprints throughout a book. The book may have any number of pages. The whole book contains 180 misprints. It is not given 180 misprints per page. Whole book, they have given the information. Now, a book has 150 pages. So, can we say in total the 150 pages have 180 misprints. 180 pages have 150 misprints, right? So what is the number of misprint per page that we have to calculate here? That is, if there are 180 misprints per 150 pages, then how many misprints are there per page, in a page, right? Then after that, find the number of pages. Once again, we must use a capital letter N into probability. Find the number of pages which contain question number 1, no misprints. No misprints. So here, what X indicate? X indicate the number of misprints, right? Here we are dealing with the number of misprints, and we have seen the example for Poisson variate, number of print mistakes per page. The same example here we are going to deal. So number of misprints or print mistakes per page. In both the questions we can observe misprints. Once again, at most 2 misprints, right? So we are dealing with here number of misprints per page. Then totally among 200 pages, that is they have given, this example is given to find the value of parameter, and they have given, suppose there are 200 pages, in how many pages we are going to expect no misprints and at most 2 misprints. So here 200, it indicate capital letter N, right? And this 150 and 180, this information is given to find the value of lambda. Here lambda is directly not given, we have to calculate. That is the difference between this and earlier problems. So here first, what to write first? Before starting, there are 2 questions to observe. First sub-question is no misprints. No misprints is 0 misprints, right? 0 misprints. And the second one, at most 2 misprints. What is at most? At most is less than or equal to. At most is less than or equal to. So X is less than or equal to 2. We have to calculate. And both those probabilities must be multiplied by capital letter N to find the answers. Right? So let us start. First, let X denote let x denote the number of misprints per page. Observe, I wrote per page because finally they have asked find the number of pages they have asked. So we have to deal with the per page, right? That is how to understand the problem. So number of misprints per page. Then x follows Poisson in bracket lambda equal to. How to find the lambda? That is here it is a very simple calculation. We have studied in lower classes. That is suppose 150 pages have 180 misprints. This is a syndicate page. This is a misprints. Number of misprints. One page has how many misprints, right? That is 180 divided by 150, which is equal to 1.2. This is actually lambda, right? This is how to find a lambda. That is here you can write lambda equal to 1.2. Next, the probability mass function is given by P of x is equal to e power minus lambda power x divided by x factorial. X is equal to 0, 1, 2 up to infinity, which is equal to e power minus 1.2 power x divided by x factorial. X is equal to 0, 1, 2 up to infinity. Now I got the probability mass function. Next, let us solve the first question. Also we can write here given n equal to capital letter N. It is equal to 200. N equal to 200. Right? Next, let us continue the first part. First question. Question number 1. Probability of no misprints. No misprints, which is equal to probability of x equal to 0, right? Which is equal to e power minus lambda, e power minus 1.2 power 0 divided by 0 factorial, which is equal to e power minus 1.2, that is a 0.3012 into 1.2 power 0, 1 divided by 1. The answer is 0.3012. Next, to find the number of pages. Therefore, expected number of pages contain no misprints. Is equal to n into p of x equal to 0, which is equal to capital letter N, that is 200 into p of x is equal to 0. This probability 0.3012. No misprints. I used this term and the answer, which is equal to 60.24. That is approximately equal to 60 pages. That is among 200 we can expect 60 pages do not contain any mistakes, right? Next question. Question number 2. Probability of at most 2 misprints. Probability of at most 2 misprints, which is equal to probability of x at most less than or equal to 2. At most 2 less than or equal to 2. Now look at the range 0, 1, 2, 3 up to infinity, right? And we want the values 2 and less than 2. 2 needed and less than 2. That is, we want the probabilities of 3 factors, right? 0, 1, 2. We can write P of x equal to 2 plus P of x equal to 3 plus P of one more term. We must start from 0. That is, first one is 0 we want. Next one, next P of x equal to 2. Let us continue that. the values 0, 1 and 2 in the probability mass function, which is equal to e power p of x is equal to 0. Already we have calculated, that is 0.3012. Directly I am going to write. Next, p of x is equal to 1. That is e power minus 1.2. 1.2 power 1 divided by 1 factorial plus e power minus 1.2. 1.2 power 2 divided by 2 factorial. Right? Next, which is equal to 0.3012 plus here 0.3012 into 1.2 second factor plus e power minus 1.2 0.3012 into 1.2 square, that is 1.44 divided by 2 factorial, 2 into 1. Right? Now simplify that. The answer is simplify these factors. You will be getting the answer 0.8795. Simplify it properly, you will be getting the answer. Next, therefore, the expected number of pages contain at most 2 misprints. At most 2 misprints is equal to n into p of x equal to, not equal to, x is less than or equal to, which is equal to n, capital letter N, 200 into 0.8795, which is equal to 175.9, which is equal to 176. That is among 200 pages, we can say 176 pages contain at most 2 misprints. At most 2 misprints. This is how to solve the problem. Next, let us solve a problem on Poisson fitting. The same procedure as binomial, right? Binomial problems we have solved. In the similar manner, let us solve the problems on Poisson fitting. One of the problem I wrote here, that is to the following data, fit a Poisson distribution and find the expected frequencies. I wrote the problem, the table will be given, and here fit a Poisson distribution and find the expected frequencies, means we must write the table. Always fitting means at the end we must write the table which consists of theoretical frequencies, observed frequencies as well as the values of the variate. Now here there is a table which has 2 rows. First row, number of printing mistakes. Number of printing mistakes per page, that we have to understand by looking at the table. It is given number of pages. So actually these values indicate the number of printing mistakes per page. It is not about per page, right? In a page, some pages have 0 mistakes. Totally how many pages are there where there are no mistakes? 42. 33 pages have 1 mistake. 14 pages have 2 mistakes, and so on. That is why observing a particular situation, they have given one observed frequency distribution. For this, we have to fit a Poisson distribution. And always the parameters determines the any distribution in a proper manner. So first we have to see whether lambda is given or not. Sometimes lambda will be given in a problem like this. Average number of mistakes per page are observed as 1.2. Something is given. At that time we have to consider lambda equal to that given value. But such problems are not considered in your book. Now here, since lambda is not given, we have to find the lambda first by equating the theoretical mean with the observed mean. Now here, observed mean we know how to find the x bar. The same thing here also we have to do. But what is theoretical mean? In a Poisson distribution, the theoretical mean is lambda. So we have to consider lambda equal to x bar. Now let us start. Always the problem we have to start by defining x. Let x denote the number of, this is x, remember this is x always, and it is a f. So let x denote the number of mistakes per page, right? Per page. Number of mistakes per page. Next, therefore, here next actually you have to write x follows a Poisson distribution with the parameter lambda, but here lambda is unknown. Therefore, first we have to find the observed mean x bar. Here we can write here lambda is not known. Lambda is not known. So find this by calculating x bar. So next we can write a table that is x, f, and next we have to write fx, right? And here what is fx? I am going to write here only. Fx values are 0 into 42, 0. Next 1 into 33, 14 into 2, 28. Next 6 into 3, 18. Next 4 into 4, 16. 5 into 1, 5. And to get the total here, you will be getting 100. That is 20, 50. Okay. 0, 33, 28, 18, 16 and 5. Okay, the total is 100. Here, this total is considered as a n, capital letter N, and it is sigma fx. Sigma fx. Now first we have to find x bar. That is here x bar equal to sigma fx divided by capital letter N, which is equal to sigma fx 100 divided by capital letter N is also 100, which is equal to 1. Therefore, x follow the Poisson in bracket lambda equal to 1. Next, right? The probability mass function is p of x equal to e power minus lambda, lambda power x divided by x factorial, x is equal to 0, 1 to up to infinity, which is equal to e power minus 1, 1 power x divided by x factorial. This is how to write the probability mass function. After that, I write the frequency function. Same procedure, that is the frequency function is Tx is equal to n into p of x, which is equal to n. Yes, here capital letter N is 100 into p of x, e power minus 1, 1 power x divided by x factorial, x is equal to 0, 1 to up to infinity. Now, this term we have to use for finding the theoretical frequencies. Next, start one by one. First, put x is equal to 0 in this frequency function. So first, put x equal to 0 in this frequency function. T0 is equal to 100 into e power minus 1. E power minus 1 is 0.3679, right? Into 1 power 0 divided by 0 factorial, which is equal to 100 into 0.3679 into 1 power 0, 1 0 factorial 1. So this you must multiply, and the answer is 36.79. It is the first frequency, right? Next, we must use the recurrence relation between two successive Poisson theoretical frequencies. Because of use of theoretical frequency, use of recurrence relation reduces our work. And we know here very simple recurrence relation is that is a by recurrence relation we can write Tx is equal to lambda by x into Tx minus 1. It is a very simple relationship, and the remaining theoretical frequencies we can calculate easily with the help of this reference relationship. Now next, in the reference relationship, put x is equal to 1. So put x is equal to 1. You will be getting T1 is equal to lambda by x. Lambda we know in this problem lambda is 1 divided by x is also 1 here into T 1 minus 1 x minus 1, that is 1 minus 1, which is equal to 0. This implies T1 is equal to 1 by 1 into T naught, just obtain the frequency, that is a 36.79, which is equal to 36.79 itself. Right? Next term. Put x is equal to 2. T2 is equal to, once again, lambda by x. Lambda is 1 divided by x is 2 into T x minus 1, 2 minus 1, that is 1. This implies T2 is equal to 1 by 2 into T1. T1 is a 36.79. Get the answer here. The answer is 80.395. Next, put x is equal to 3 in the recurrence relation. T3 is equal to lambda. Lambda is 1 divided by x. X is 3 into Tx minus 1. 3 minus 1, that is 2. This implies T3 is equal to 1 by 3. Right? Into T2. T2 is 18.395, which is equal to, that is now 18.395 divided by 3. Simplify that, you will be getting 6.1317. 1316. Okay. Next put x is equal to 4. T4 is equal to lambda 1 divided by